the photoelectric effect demonstrated that light had particle-like properties in that it was made up of bits, photons, that carried momentum with them, which we've been calculating like so. Now, light had been considered purely a wave phenomenon for hundreds of years, and so this was troublesome, to say the least. But the thing about troublesome ideas, when they pop up and then are demonstrated to be true with experiments, is that they start opening up other things that we've maybe assumed are true to some speculation and questioning. So this cat up here, DeBroglie, saw that stuff about light and said, well, if light can have particle properties, well, maybe particles can have wave-like properties. And so taking just very simple relationships, right? The momentum for a wave-like light and the momentum for a particle-like, like an electron or a ping pong ball. And he said, well, what if I just hooked them together and did this sort of thing? And then I could move my wavelength up there and move my MV down here. So I get something that looks like this. Okay, cute, right? Like, it's just an equation, no problem. But if you think about what that's saying there, it says that anything with mass and a speed has a wavelength. Anything. So that's crazy, right? Do you have a wavelength? Are you a wave? If it's a wave, then wave properties are things like reflection, refraction, diffraction. So this is implying that not only would light reflect, refract, and diffract, but also particles should be able to do that as well. Because any particle with mass and speed should have a wavelength, if that's true. So for an electron, for an example, consider an electron. Okay, and we'll let it traveling at, let's say, 0.3 C. Well, if I put that in there, then all I need to know is the mass of an electron, which happens to be 9.11 times 10 to the negative 31 kilograms. These are facts that I have tattooed on the inside of my eyelids from my physics degree experience. It haunts my dreams. Anyway, if I'm going to put that mass into here and that speed into here, and I'm going to remember that the Planck's constant was 6.63 times 10 to the negative 34 joule seconds. If I pop those numbers into there, my wavelength for that electron should be 6.63 times 10 to the negative 34 divided by 9.11 times 10 to the negative 31 times 0.3 times the speed of light, which is 3 times 10 to the 8th. Alright, and if I can ever remember to bring my calculator. Alright, let's see, 9.11 times 10 to the negative 31 times 0.3 times 3 to the exponent 8 gives me 6.63 times 10 to the negative 34 divided by 8.199 times 10 to the negative 23. Put that in the denominator, multiply it by 6.63 times 10 to the negative 34, and I get 8.086 times 10 to the negative 12. that number is small. When you get down to 10 to the negative 12, you're starting to talk about the size of a nucleus. So that's pretty small. So with a wavelength that short, you're not going to see that property because it's so tight. Now, that doesn't mean it's not there. It just means you have to set up an experiment that's fine enough in order to get those sorts of wave behaviors to show up for a wavelength that small. Now I just picked 0.3 C just as a random number just to show you how that would work. But if we picked anything smaller than that, so a less fast speed, the smaller this speed is, the bigger this wavelength gets. So that this can actually start to show up as something that we could observe. So, okay, so an electron's got a wavelength, fine. What does that mean? Well, I think if you've taken chemistry, then you've seen a diagram of hydrogen that looks like this. You've got a positive in there, and you've got an electron in an orbit, like so. And if you've done some more chemistry, then you know that these electron orbits, they have different ones. They have the resting orbit, and then there's a first excited energy, and then there's a second excited energy. And maybe you've wondered, well, why? Why are they like that? Well, after a bit of experimentation, this is a Bohr model. It turns out that this thing here, this is exactly one wavelength of an electron traveling at the appropriate speed, and this here is two wavelengths traveling at the appropriate speed, and this would be three wavelengths traveling at the appropriate speed, etc., etc., etc. So this sort of wacky notion that an electron has a wavelength actually fits pretty tidily with the Bohr model of an atom. And when we get to the electromagnetism unit, where we can actually talk about electrostatic attraction forces, we're going to work out the radius of these orbits. But for now, the wave property that this relates to is when we're blowing air over a tube to make it hum at certain frequencies, okay, resonance. That when things are the right length, when they're full integer wavelength lengths, the wave, it creates a standing wave. You may have also seen this on a jigsaw with a wire, which is pretty fun to watch. But the thing about waves is when you have standing waves on these green lines, you have interference patterns in between them. So the wave is interfering with itself, which means that the electron can't manifest there. So it's not that it's not there, it's that it's interfering with its own wave in between these lines. So an electron can't be here because its wavelength causes an interference pattern. It can only be on this convenient little track, which means that electrons can't travel from here to here. They are either on ring 1, ring 2, or ring 3, and in order to appear on those, they have to jump. They can't travel there, which introduces this whole other bonkers set of ideas where the amount of energy they can absorb or send out as they jump through these layers is quantized, right? It's a chunk. Right? The energy that they have here and the energy that they have here, it either has that much energy or it has that much energy. It never has a value in between. So if it needs to absorb or shed energy, it can only absorb or shed energy in those very specific chunks. And if you were to pick up a diffraction grating and look at a fluorescent tube, you can see the color lines of these electrons jumping back and forth between these particular orbits, which is like a really easy, right in front of you experimental justification for this really ludicrous idea that electrons are either here or here and never in between. And that in order to travel from here to here, they have to pop out of existence and then reappear at the new location. So that maybe, while you can't see it quite here in the math, because the math isn't too terribly complicated, is maybe the most weird of all the weird things. That matter doesn't matter. The matter isn't really there. It's waves, just like light is waves. And so when you touch something, you're not really touching something that's there, you're touching something that's probably there based on its wavelengths. So I'm going to let you stew on that for a minute. We will circle back to this orbit stuff when we get to the next unit. There are a few problem sets to try. It's just a little bit of calculation with this very simple formula on a sort of big idea. So this here is the beginning of quantum mechanics, right? The idea that small things, because their masses are so small, end up making wavelengths that are actually workable and have wave properties start to appear for them. We did relativity, which is when massive things get going at very high speeds, then rules of time and space start to bend. And what's left is the space in between, right? That space in the middle where things are not huge and very fast, but are also not very tiny. So our existence, like the length scale that we live at, is too big for quantum mechanics, but it's too small and slow for relativity. So these ideas, while they seem really crazy, only seem crazy because we're the wrong size. If we were bigger, they would be obvious parts of our existence. So the forefront of physics then, right now, is trying to unify the two, trying to find a way that these quantum properties extend through us, through things our size, into the very large, and how relativity extends from the very large down into the very small. And there's lots of people working on both ends, chewing away, and eventually, hopefully, they'll meet in the center. And then all sorts of crazy things become possibilities. Okay, so I'm going to leave you with this. Good luck with the problem sets, and we will return for electricity and magnetism.